Hello and welcome to this tutorial in the Introduction to Numerus series. Numerus is a multi-purpose modeling program that lets you design and run your own models using one of a number of different paradigms. In this tutorial, I will go through the steps of building a logistic population growth model. Logistic growth is an example of growth that has an upper limit. It is often called density dependent, in that the growth rate decreases as the population approaches a certain asymptotic value, which is called the carrying capacity. If the population gets above the carrying capacity, the rate of change becomes negative and the population size drops back down to the carrying capacity. We see this type of upper limit on growth in a variety of fields, including chemistry, physics, and economics. As in the earlier tutorial on population growth, if we are dealing with a biological system, we will allow for fractions of the population size, even though it doesn't make sense to have a fraction of an individual. We can measure the population size in terms of a quantity in which fractions are not a problem, such as biomass measured in kilograms or metric tons. Once again, we're going to presume a constant intrinsic growth rate. Intrinsic growth simply means the maximum growth rate in the absence of any constraints. You could think of this as a fertility rate, and we are going to say that this doesn't change over time. Now, animals have many adaptations to deal with resource scarcity, but for starters, we can assume a fixed carrying capacity, and maybe later build a more complex model in which the carrying capacity depends on other factors. I'll talk about the different ways you can represent time in a model in another tutorial, but for right now, what's important to know is in order to model time continuously, we need to come up with an equation that poses how the population is changing at any particular moment with respect to time. In other words, the instantaneous rate of change. Let's begin by looking at the differential equation for unbounded population growth, which you may remember from an earlier tutorial. P is the total population size, and dp dt is simply r times p, where r is the intrinsic rate of growth, which you can think of as a per capita growth rate. If r is greater than 0, then dp dt will always be positive, and the population will be growing without bound. If r is less than 0, the population growth will be negative, and the population will then decline to 0. Now suppose we introduce a positive carrying capacity K. If P is much smaller than K, the system should operate much like the unbounded system. If P is much larger than K, then it should similarly operate like the unbounded system, but with declining population. Finally, if P is close to K, then dp dt should be close to 0 and get even smaller as the population approaches K. This equation fulfills our requirement. Notice that if P is small compared to K, the term P over K is small compared to 1. And the equation is close to that of the unbounded system. If P is larger than K, then P over K is greater than 1. And the right-hand side of the equation is negative. When P is close to K, and then P over K is close to 1, either slightly larger or slightly smaller, depending on whether P is greater than K or P is less than K. And as P approaches K, 1 minus P over K approaches 0, which means less and less change. There are actually many equations that produce a system operating along the same lines. This particular one was devised by the Belgian mathematician Pierre-François Verhulst in 1838. This equation fits well with a much larger mathematical framework and so has persisted in popularity. So let's start by dragging the required components to the modeling canvas. As before, we will use a stock, called P, and a flow called change P to represent the population and its pattern of changes. And we link the output of change P to P. Now we anticipate that we will want the ability to vary in the running model the values of the intrinsic growth rate R, the carrying capacity K, and the initial population init. So rather than use terms, we'll drag 3 sliders onto the canvas to fill these roles. Before continuing, this would be a good opportunity to save our work, which we'll do as we did in the earlier tutorial. Now we'll add connectors to show the interdependencies of the model's components. Our equation tells us change P requires R, K, and P, and that P requires init for initialization. Now we're ready to program the components. We first insert the right-hand side of the differential equation as the value of change P. We can either type this directly or use the connections menu created by adding the connectors to form the equation. We'll do the latter to show you how it's done. Notice that as we use the dependencies in our equation, the dotted line connection turns to a solid line. Now let's set up the sliders. We need ranges, step sizes, and initial values for each of them. My choices at this point are pretty arbitrary, but in a model of a real system, these would depend on the nature of that system. So I'll use values of R that range from 0 to 1 with a step size of 1/100th and an initial value of 1/10th. Since K can't be 0, we'll let it run from 1 to 500 with a step size of 1 and an initial value of 100. Lastly, we'll start with an initial population of 10, with a range of 0 to 1000 and a step size of 1. Now we haven't yet visited the stock called P to specify an initial value. Once again, we see that the connection from the init slider to P is listed in the connections list. But let's see what happens if we forget to make this entry and proceed to launch the simulation instead. We cannot launch the simulation until we fix this. Notice that including the connectors enforces some degree of model correctness, since it requires that we use everything we say we're going to use. We make the fix, and before launching the model, we need a display for showing the results. We'll use a line graph once again to graph P, and we'll start out with this graph configured to show comparisons. Let's save the model and set up the simulation parameters. The simulation will run from 0 to 100 with a dt of 0.1 and integration method RK4. And now finally we launch and run the model. See how this graph looks exponential to start, but soon begins to approach the carrying capacity of 100. Sweeping across the graph shows mappings of individual time points, and switching to the table view presents all of the output. Now let's change the value of R the growth rate, to 0.5 and run the model again. As you could predict, the population grows more quickly, but still levels off at 100. And it does this even faster with an R of 0.75. Now let's change the carrying capacity to 200. Growth proceeds at the same rate, but levels off at 200. Finally, we'll start with an initial population of 500 and the same carrying capacity of 200. Now the graph shows a declining population which is approaching 200 from above. The sweep and tabular view show all of the values, and the size of the display can be adjusted so that we can see all of the columns in the table. The contents of this table can be saved in a list of comma-separated values. Before we go, there's one final thing to look at. Returning to the design frame, I'll make a small change to the graph so that it displays continuously throughout the run rather than only at the end. And then once again, I will launch the simulation. Now I will check the box labeled Debug, do a reload, and then reduce the simulation speed a small amount. After making an adjustment so that you can see everything, watch what happens when I run the program. All of the component values appear on the design canvas, and we can see how they change. I'm sure you agree this can be very useful information while you're building your model when combined with single stepping. This completes this tutorial, and I'll see you next time.